Dear students, today through this video I would like to share with you one of the very basic concept from structural design of reinforced cement concrete or our own RCC. So all the calculations in this particular video will be based on the Indian Standard Code IS 456 of concrete design. This can be further extended to any code of practice that follows limit state approach of design. So here we are going to discuss in detail the derivation of moment carrying capacity of single reinforced beam, the assessment of neutral axis depth, and also the very basic assumptions that we make as engineers to simplify complicated calculations. When this particular course was introduced to you in your undergraduate level, the trainers who helped you in understanding the concept might have used 2D images which are either drawn on blackboards or projected on a screen. But the problem with that, there is a limitation in understanding the orientation of the fibers. A proper understanding of this orientation is all you need to appreciate the beauty of this derivation. So with a small introduction, we are jumping in to the core part. So let's watch what is happening here. So what we have here is a beam, okay? A beam having length L and overall depth D, width B. And due to the action of some flexural load, it has got a profile like this, which is the profile after bending. So what we are going to do here, we are going to cut a section. When I say a section, it's not simply a cross section. I'm cutting a portion of the beam as in the figure, and I'm going to analyze that particular portion for the further derivation. So moving on, I'm considering the section that is cut. Okay, so this is the one that you all are very familiar of. This is the cross section with which we will be starting the derivation. But the problem with this particular cross section is it's in 2D. Okay, and I will tell you what happens when you view it in 3D. So I will just introduce you the different portions. So one is this green zone, which is basically the zone which is under compression. This red zone is the zone which is under tension, and you have the steel represented. The area of steel is taken as AST. So the depth from the top or the fiber which is under compression to the fiber which is not undergoing tension or compression is called as the neutral axis depth, normally represented by XU. And this is the effective depth, which is the distance from the top fiber or the compression fiber to the CG of steel, that is the effective depth. And this particular line which passes through the fiber which is not undergoing tension or compression is called as the neutral axis. But the problem when this was introduced was that students used to have a tendency to assume that the fiber which the trainer is talking to you is this one. Okay, we tend to believe that this is the fiber under consideration, but that is the point where we are all going wrong. The fiber is not this. Okay, the fiber is actually on the other plane. So this is the beauty when we think this particular problem in 3D. Okay, so you can see here, because of the action of this bending, you can see the beam is bending. So this particular portion what we have taken, it will also be bending into a profile which is shown by this dotted lines. So you can see here, these are the different fibers. The orientation of fibers is in this direction. All the derivation and the next calculations are based on this cross section rather than this. So you can see here, the top fiber which is under compression means that it is getting shortened. You can see earlier the fiber was having a length of this much, and now it got reduced to this much. Similarly, the fiber in the bottom which is under tension has got elongated from this length to a length denoted by this dotted line. And this is, of course, this is an enlarged view. This is not the actual displacement. So just for understanding, we have given an enlarged view for the displacement. Now we know there is a fiber which is at the level of neutral axis which won't be undergoing either shortening or elongation. this fiber that is marked in white color is that fiber. So the neutral axis what we are talking is not like this. The neutral axis is actually in this direction. So further moving ahead, we are going to first discuss about the basic assumptions, and then we will start the derivation procedure. So these are the two things that we need to know now. The first one is actually this concept, the concept of linear strain. Linear strain is change in length by original length. Okay, so if a fiber or a rod is having one particular length, and because of the application of a force, it reduced its length. Okay, what happened is shortening, which means the length has got reduced. So this particular rod or fiber will be subjected to a compressive strain, and if the length is extended or elongated, there will be tension. So that is this particular concept. Then we are thinking about the important assumptions. So the first thing is plane section remains plane. You will be very familiar with this term because in Euler-Bernoulli beam theory, this is the very first assumption. So what does it mean? Plane section remains plane. It finally ends up giving us this conclusion that the strain is linear, which means that you can see here the different fibers are getting shortened in such a way that this final line is a linear line or a straight line. So you can see here I have used a different representation for this same. Okay, so this is the original section, and the top fiber got reduced, the bottom fiber got extended, and this is how the linearly the strain is varying or the displacement is varying. This is the deflection that is happening for the fibers. So you can see here it is a straight line. That is what meant by strain is a linear concept. The second one what we are considering is the tensile stress in concrete is ignored, which means that the concrete is there both in the compression zone and in the tension zone. Everywhere we are having concrete, but we assume that the concrete in the portion which is marked in this red, which means the concrete in the tension zone is cracked, which means if something is cracked, it won't be able to take any more tension. So we generally tend to ignore this to simplify the calculation. And the third one is this one. And what is this? We will discuss in detail when we start seeing the stress block. So this is particularly the strain. So when we deal with the stress and strain curves, which we are going to do in few minutes, you are going to understand that in detail. So from this, we are moving to the strain diagram. So we have the deflection diagram. From the deflection diagram, we are moving to the strain diagram. To plot the strain diagram, we require these two graphs which are provided in IS 456. Okay, this is the stress strain curve for concrete, and this is the stress strain curve for steel. These are idealized curve. So in bold, you can see a design curve. So whenever we are going for design, we should use this curve. That's what is intended by providing it as the design curve. So in the x-axis, you can see the strain values. So when the strain is 0, the stress value is also 0. And as the strain increases, the stress also increases. The initial increase is in a parabolic fashion. And when it reaches a strain value of 0.002, the stress value is 0.447 FCK. Okay, that is the stress value. And on further increasing the strain value, you can see that the stress value is not changing, it remains constant. And finally, when it reaches a value 0.0035, we assume that the concrete fails. So the concrete can take a maximum strain of 0.0035, and the corresponding stress at that time is 0.447 FCK. So this is what the behavior of concrete is. So that's what we are going to plot first, and then we will move to the steel part. So you can see here in the deflection, okay, in the deflection of fibers, this fiber is undergoing the maximum deflection. So just before failure, so first one to fail will be this particular fiber. So just before failure, the value will be the maximum strain, which is 0.0035. So I can directly represent the strain value at the top fiber as 0.0035. And this is the neutral axis fiber, which is neither undergoing any tension or compression, which means that the strain value is 0. Okay, and in between we have the assumption strain is linear. So I can connect them using a straight line, and I got the compression zone strain diagram. And I have marked this 0.002 in between. Okay, this value is 0 at the center or the neutral axis, and the maximum is 0.0035. So definitely I'm going to get a value 0.002 in between. The relevance of this point is that From this point, there is a variation in the behavior of the stress. Okay, up to 0.002, from 0.0035, the stress is constant, then it varies parabolically. So when we go for the stress block, we will come to know why or what is the relevance of this 0.002. Now we are moving to the tension part. So for considering the tension part, we are ignoring the steel. So in the tension, we are ignoring the concrete, my mistake. So we need to think about the stress strain curve of steel. So you can see here, this is the stress strain behavior of steel, and we have the design curve. So you can see here, it is said that in the assumption also it is said that at the time of failure, strain in steel fiber should be some particular value. It is given here, and you can see in the stress strain curve that value is given. Okay, this is basically the yield strain. So any value less than this, we consider it is not yielding, but any value greater than this particular value which is given here, steel is yielding, which means it elongates, okay, without an increase in the stress. And we can see here stress corresponding to this particular strain is 0.87 Fy, which is available in the stress strain curve. So this is the minimum strain. So definitely by the time the concrete reaches the strain 0.0035, steel fiber has to reach this particular strain. So that's what we have marked here. That is 0.002 plus 0.87 Fy by Es, which is directly available from the stress strain curve that is available in the code. And one more thing I want to tell you, we are doing all this calculation considering a unit width. Okay, we are considering a layer. This whole cross section is having a width of B, and considering a small layer. Okay, a small layer I'm considering which is having a unit width for the rest of the calculation. So unit width is given here. So our strain block is also having the same unit width. Okay, so with this we are moving further ahead. So now we are going to think about the stress block. Okay, so we are moving from the strain diagram to the stress diagram. So here we'll be using these two graphs, this stress strain plots, for getting the different values. So you can see here, corresponding to a strain in concrete of 0.0035, we have the stress as 0.447 FCK. Okay, 0.0035, the stress is 0.447 FCK. So the top fiber, I can give a stress of 0.447 FCK. Similarly, now we can see the strain is decreasing and it reaches a point 0.002 as the strain value. For strain corresponding to 0.002, it is also 0.447 FCK. So I will be having a rectangular variation, or it will be a straight line from this fiber to the fiber which is having a strain of 0.002. That's why we are getting a rectangle in this portion. And then it goes to 0. And the variation is parabolic in our curve, stress strain diagram. So that's why we are having a parabolic curve in this portion. Now before jumping to the stress in steel part, I'll be explaining a bit more about this stress block in compression. So we are seeing some things written over here. Okay, let's see what those are. So the first one is area of stress block. So what I'm doing is I'm calculating the area of this green zone. Okay, what will be the area? This area of rectangle plus area of this parabolic area. When I do the calculation, I'm going to get the value as 0.36 FCK times XU. And if I'm looking into the unit of FCK, which is stress, and this is length. Okay, XU is the depth, which is the dimension of length. So this is Newton. Say if I'm taking the units as Newton and mm, so it's going to be Newton per mm square, which is the stress, multiplied by mm. Now I know that the width is 1 unit. If I multiply that also, I'm going to get the volume of this stress block having unit width. So what will be the volume? I'll be multiplying again with 1 because this dimension is unity. So I'm going to get Newton per mm square multiplied by mm multiplied by mm, and that's my force. Okay, basically stress multiplied by area is going to give the force. So this particular value what I'm having here is the force or the compressive force, as this is a zone in compression, the compressive force for a unit width. That's what this particular value is. Okay, and you are seeing two parameters here. One is 0.42 XU. That is basically the location of CG. Okay, the CG of this whole block will be somewhere here. So the depth of CG from the extreme fiber in compression is 0.42 XU. So you can do that by using calculation. You know how to calculate CG, you will get that value. And now I'm moving to the tension part. So in tension, the strain value is 0.002 plus 0.87 FYES. And if I refer to this particular stress strain curve of steel, I'm going to find that the stress corresponding to a strain of this much is 0.87 Fy. So I'm directly plotting the stress value as 0.87 Fy. And now we can think about this d minus 0.42 XU. Okay, that is basically the distance between the CG of the compression block and CG of the tension block, which means that this is basically the distance between two forces. Okay, so this is d minus 0.42 XU, which is going to act as the lever arm when we are calculating the moment carrying capacity, and that we will do in the next step. Okay, so we are moving for that. So once we have this, we are moving to the final part, which is the calculation. So now this was done. Okay, this stress block was drawn considering a unit width. If I'm considering the whole width, I'm going to get a diagram like this. So for a unit width, I have the value as 0.36 FCK XU. When it is having a width of B, I just need to multiply with B and I will be getting the compressive force contribution of this whole concrete. So the compressive force is 0.36 FCK XUB. Similarly, the stress in steel is 0.87 Fy. If I want to get the tensile force, stress times area. The area of steel is AST. So if I multiply 0.87 Fy with AST, I'll be getting the tensile force. So now I have the tensile force and the compressive force. Okay. Once I have that too, that's the end of the theoretical background. Now you just need to use some mathematics and will get everything what you want. So first we know that this is a system which is in equilibrium. A system is in equilibrium, every part of the system will be in equilibrium. Now we have two forces, one is a compressive force, other one is a tensile force, which are basically opposite to each other. One is compression, other one is tension. So it is more like you can equate this tension and compression, because if the system has to be in equilibrium, the forces should be in equilibrium. So I can equate tension and compression. So the compression is 0.36 FCK XUB, that I can write here, and the tension is 0.87 Fy AST. Just equate this and I can get the value of XU, which is basically my neutral axis depth. Okay, and similarly, if I want to calculate the moment of resistance or the moment carrying capacity, we know that moment is calculated as force times lever arm. Okay, and the lever arm part we have already calculated, which is d minus 0.42 XU. What about the force? The force is either the tensile force or the compressive force. Both are having equal magnitude. So if I'm calculating it with respect to tensile force, it's 0.87 Fy AST, which is my tension, okay, multiplied by lever arm. Lever arm is d minus 0.42 XU. Or I can use the compression value, that is 0.36 FCK BXU times d minus 0.42 XU. So this is the expression for moment carrying capacity. This is the expression to find out where the neutral axis is. And with this, we are coming to an end of this particular video. If you happen to like this video, do subscribe and share it to your friends. The subscription will help you to get notified with the further updates on other videos I'm preparing on this similar topics. Thank you.